everyone. We're the Mind Tracker group, and this is our final presentation. So we will be covering different topics, starting with a brief introduction and ending with the future plans to possibly improve our project. So as you all know from our last presentation, the U.S. Bureau of Labor Statistics identifies mining as a very dangerous industry to work in. And our goal was to try to minimize any kind of danger by providing a tracking system for mine workers and also wireless communication.
To discuss the system of the mine tracker, it has three components. There's an endpoint, which would be worn by any mine personnel or placed on any type of equipment within the mine. There's the router, the ZigBee router, which would identify where these different devices are. And then there's the coordinator, which collects all the information and displays it on our end web application. The typical use case for this will be in a room and pillar coal mine. This is the layout of a room and pillar coal mine, and it would have the three components throughout. As you can see, there would be a web application hosted on a computer that's utilized by an administrator. Then there would be the black device on top, which is the ZigBee coordinator. Then that would be connected to the routers throughout the mine, and then each miner or equipment would have a miner endpoint assigned to them. The estimated cost for all three components total with our final project would be $80.93. Just a regular walkie-talkie system for about 12 users is in the thousands of dollars. That's something that's effective for a mine. And this is a scalable design, so there would be multiple endpoints, multiple routers. And they're at low cost, each of $25 and $30.
So because we are intending to work in mines, we have to research whether our devices can communicate over long distances. So we decided we had to conduct a range test. We decided to use Kelly Commons because it was the closest location that emulates the conditions of the mine due to it being pillars, having a large amount of traffic, and also having low network connections. So what we had to do, basically, we had a stationary device which acted as a coordinator. We had a mobile device that acted as our endpoint. We kept moving from different distances using different powers to see how much connection strength we got back. So for example, for this one we moved 60 feet using the power of 15 watts. We sent out 1,000 packets and got back 316, so we have a pretty high connection strength at that moment. These are other examples of different distances and powers that we use throughout, and they all pretty much show the same result. So that these separate boxes are the first three will be 60 feet, the second one is 90 feet, and the last one is 110 feet. Different powers showing how much signal strength we got back. So what this basically shows us is that no matter where we are in the mine, hypothetically, we get just as much as we have significant enough power, we can always have enough communication that allows our goals to communicate.
So firmware, when working with the NXP development boards, we need to decide what IDE we wanted to use. IDE is an integrated development environment, and it's what we use to put the code onto the board. We decided to work with IAR, Embedded Workbench. Other software tools we used were TestTool 12 and Kinetis SDK, which came with different firmware packages, and example codes that we can use to kind of figure out the board more. This is just a video of our phase 1 progress, which was just becoming more familiar with the board and like connecting an LED to a push button. This is just the sample code that we used for it. It's really simple stuff. The next, for phase 2, we wanted to establish board-to-board communication, and we do that by putting a home automation profile for on and off, switch on one of the boards for a push button, and having another board have the home automation profile for on and off light. And this is the example code for it, just a screenshot of what it looked like on the IDE.
Now for two ZigBee boards to communicate to one another, we set up one as a router and one as the coordinator. To initialize this communication, you need to start running the networks on both of the devices. Then once the networks are running, which we did by initiating a simple push button, you have to start both devices searching for each other. We did that by initiating a long press on that push button on both devices. Then once they pair, you'll see the flashing lights on both devices stop. Then we'll be able to control one device wirelessly, but using the push button on the other, which we'll see in this example. So now the network's running on one of the devices. Now it's running on the second one. Now it's starting the search process for another device with the flashing light, and we're searching on the other device as well. Once they pair, it stops flashing. And now you can see we're controlling one board with the other push button on a separate board wirelessly using our Zigbee network.
Next, I'm going to discuss the hardware design for our project. So what we use the Freedom Development platforms, and we placed one each on each of the 3 components for our line tracker. We also included an ultrasonic transceiver on the router, and we used 2 different kinds of power supplies. We used 3.7-volt lithium batteries and a 5-volt wall adapter. And lastly, we used Altium for our schematic and our PCB drawings. So, as mentioned before, these boards can use Zigbee, so that allows for wireless communication. And they can also be powered in 3 different ways. First way through micro USB, second with the headers, and third with an external DC supply or an adapter. And I put these ports in red because these are the methods that I used for powering the boards. And these are the headers that I circled over here. This one is 3.3 volts, and the other one is the ground that I used. This is the endpoint schematic drawing. It has the 3.7-volt lithium battery, and I included a voltage divider with all of these resistors to reduce the voltage to 3.3 and to power the board. This is my PCB drawing, and it's the same as the schematic, but this is what we use as the blueprint for creating our PCB. Next is our router and charger schematic, and for this part I used 2 power supplies. There is the main supply, which is the 5-volt wall adapter, and it's the part on the top. And we use the backup 3.7-volt lithium battery, and that's located over there on the bottom. And again, I had to use voltage dividers to reduce voltages to 3.3 volts. And lastly, I included diodes to allow for switching between the adapter and the battery and vice versa. I will explain that part later when you see the demo. And I also included a lithium battery charger. So this is the PCB drawing for the router and the charger. And here's a demo of our router circuit. So both are plugged in, the battery and the adapter. And when I unplug the battery, the board stays on. And if I unplug the adapter, it's the same thing. The board will still remain on. Then if I get rid of both, then it turns off completely. And lastly, this is the coordinator schematic. And this is the simplest one. We're just using a USB connected from a PC powering the board with 5 volts. And for creating my PCBs, I used copper boards, a hacksaw, Sharpie permanent marker, ferrochloride solution, which is the etchant, rubbing alcohol, a drill, soldering gun and wire, soldering paste, and a heat gun. And these are my design steps in detail, but to condense them, the first thing I did was I cut the boards with my hacksaw, then I drew all the designs with the Sharpie. Then I placed the boards into the etchant solution, and afterwards I just drill and I solder everything together, and I tested my boards and they worked. And these are my before and after pictures. Yeah, so before, this is when I sketched all the parts onto the copper boards. Then after I etched them into this solution, they come out looking like that.
Software. So for our software, we have the web application, and the application is
the website is published, but for the sake of ease and time, I have screenshots of it. So this would be the login. This shows a little bit about our vision, our technology, and how our interface is better than I guess our competitors. And once you log in, what you want to come to is the user interface, and it shows the line on the left and the sections of the line on the right. And on the bottom, you have a list of all the components inside of the line, all the endpoints, and it shows their status, like their entry time, the condition, the battery life, etc. For the web application and for the database, I use Visual Studio, and the main component, the main thing that I used for the database was an SQL Server database. It's very easy to configure and add new components to it, and I use the entity data model, which allows the codes from the SQL language to be translated into C, and then later used into any program that would create the visual that you saw in the previous slide, and allow us to just basically track any person inside of a line.
To conclude, we wanted to discuss different setbacks that we had. There were a lack of resources using our Freedom Development boards. There were a lack of those resources online, and we had a lack of access to those boards. We weren't able to get those boards until I think a month into this spring semester. Tutorial guides that we could find online were either outdated or applied to older different boards. And we wanted to use the NXP boards because that was more of an industry standard rather than seeing a lot of the Arduino tutorials that we could find online. And the boards themselves were not fully compatible with Windows 8 and 10, which was a common trend that we found online going through different forums trying to troubleshoot these boards or trying to fix them after we would brick them. And there was a lack of professional equipment from a hardware perspective for setting up the PCB boards. There's a lot of smaller pieces of hardware that we would have liked to use, but we don't have the equipment to properly install it. Future plans, of course, would be to complete the project into the final stages. Our goal is to integrate sonar, and we have a sonar sensor on our PCB design, but we have not been able to properly communicate with it yet. We would like to implement a Zigbee module by itself instead of having the whole Freedom Development board, which is how you would get the cost down to such a low price. And we would want to finalize proper casing for our end device, making it waterproof, making it something that is more suitable for a mine instead of an exposed PCB board. We kind of have the roadmap laid out for future capstone development for any class next year that might want to pursue this further. We've acquired a lot of expensive development equipment. These NXP boards each cost around $250, and as our group, we were able to collect about 12 of those for free. So our goal is to donate those to the school so future classes next year and years following can have this equipment totaling up to close to $3,000. Thank you.
A question on the NXP boards. I'm not familiar with them. Looks like the two previous projects also used them. Do you know if they had the same kind of problems?
We all had problems. We all kind of worked as a team. Part of the boards that we collected, we were sharing with our team members in the class. Okay. And it was a really good learning experience because the NXP purchased Freescale, so they're pretty widely used. Yeah. They're a widely used development platform. So all of us had a lot of problems with it, but it was how we kind of learned the ins and outs of the firmware of the boards.
Okay, and then I'm not sure exactly how the ultrasonic fits into this program. I know you didn't get to it, but what?
So the sonar would probably be something that's on the router side that's mounted in the wall of a mine, and there would be a set distance of what would trigger the sonar. And then once the sonar is triggered, we'd probably use the localization of the Zigbee infrastructure to say, all right, this sensor was triggered, this is the actual endpoint that is triggering it.
Okay. Thank you.
Any other questions?
Thank you.